Mr. Shantz here. I'm conscious that the people who come to class today, I guess cohort A, they were in class learning about regression in today's lesson and working on the mini project, but for the people working at home, that probably wasn't very helpful. So I'm doing this recording to kind of show you what I did during class to execute this data management mini project. So let me just quickly chat about what we need to do here. So the project says, find a two variable data set. What is a two variable data set? Well, it's kind of like how it sounds. It's two variables. There's going to be one variable that you're comparing against another. So in this case here, we say, so data set with at least 30 data points, which you think approximates a linear, quadratic, or exponential model. Yesterday's Apple share price is an example that fits an exponential model. Okay, so in terms of Apple's share price, is it one variable data or two variable data? Well, the way the share price is shown is it's the price of Apple's share on a given day. And that graph is per day. So you're showing the share price over time. So the two variables there are the share price and time. So that is two variable data. In today's class, I saw some of the difficulties around finding good data. And I wanted to allow the class to explore and find data that maybe resonated with them or something that they were curious about looking further into. And I think because of that, people spent a lot of time looking at data and not as much time doing steps 2, 3, 4, 5, 6. That's okay. Finding good data is all part of data management. And so anyways, that's a long way of me saying it's hard to do step 1. Step 2, create a linear regression, quadratic regression, or exponential regression. Again, regression, kind of a funny word. What does it mean? It's a line or curve of best fit. And we'll get into this when I actually start graphing some of this stuff. But let's first just execute step 1 and go step by step. So step 1, let's find some data. Now, in today's world, obviously, COVID-19 is something that everyone is talking about, and there is a lot of data available for it. I went to this website. I just Googled, what did I Google? COVID historical data, Canada. And then I think I also just did Googled the COVID historical data, full stop. And I got brought to some of these websites, which are a little bit messy. Then I found that the U.S. has really good data on COVID tracking. They actually have a COVID tracking project. And when I click on this link here, it brought me to this page. And you'll see I can get the data as a CSV file. I click on that. That essentially means kind of like a spreadsheet. And here's my data. It's kind of messy though. And I don't know how I'm going to get this into Desmos. And I don't even really know what I want to graph. There's a ton of columns. Okay, let me see what I can do with this. Okay, I'm going to try and get this data out of here and into Desmos. So I got Desmos set up here. And I'm not really good with Keynote, or what is this? This is MacBook's Excel, but I can definitely do something with this in Excel. Let me see if I can get that over there to Excel. Or if you're more comfortable working in a Google Sheet, actually maybe I should do that. Let me do it in a Google Sheet because that's probably what we're all more comfortable with. Okay. I should probably do this on behalf of them. Okay. All right, create a new spreadsheet. And let's see if I can copy this data in here. I just press Control V. Did that copy? No. Oh, it did copy. Brilliant. Ha. Okay. So I do have data in here. I have the date. I have all this column data. Now, really what I want to look at is, the number of positive cumulative cases. So this number, I want to know over time how the caseload has increased, the number of positive cases. Now, the difference between this column and this column is this is the increase day over day. So, on this day, 78,661 cases or positive cases was the daily case count in the US. And this number increased to this number by 78,661. Okay? I want the number of positive cases. So I'm just going to copy that column and bring it over here. The number of positive cases. And I want to know the date. So I'm going to Control C that and then paste it here. Control V, or if you're using a MacBook, it's Command V. Now, Desmos does not like date formats. So if you put this into, well, actually, let me just show you. Let me cut this, or I'll delete this. Let's put this together. What you want to do is you want to get these columns beside one another, and then I'm going to copy this column, Command C, and I'm going to put it into my Desmos by Command V. Okay, and then now I've got all this data. If I click on this plus sign, this is how it shows up. I'm expecting data for the year 2020. And this is plotting it, in 1985, 1980. It doesn't make sense. It looks really weird. I was expecting a line to kind of go like this. Up and up and up. And that's because Desmos doesn't really understand what 2020-10-28 is. So I'm gonna start a new graph. I'm gonna start fresh. I'm gonna go back to my Google Sheet. I'm gonna insert a column here. Insert one to the left. Okay, and instead of copying in the date, I'm gonna just call this day. And this will be day 0. And then I press equals. I highlight the day above and I click on +1. And then I copy that formula down. Command D in MacBook or Control D on a keyboard is Control D is down. D stands for down. You're filling that formula downwards. And then I'm going to go to the bottom.
Fatima Pryor, please go to room 104. Fatima Pryor, please go to room 104.
Okay, and now we have 280 days of COVID data. Now, what did I actually do? Okay, here's my first mess up. And again, we're working with data. We're all working with different data, so we need to think about what we're entering, what we're interpreting. What does this mean? Well, I put my days in wrong. On day 0, we didn't have 8.8 million positive cases. I did that wrong. So what am I going to do to fix that? Well, I could resort this data, or I could, actually, why don't I do that? I'm going to resort this data. So I'm going to go data, and let's see if we can sort here. Data, sort sheet by column V, A to Z. Okay, let's try that. Perfect. Okay, so now my dates are going upwards as I scroll down. Perfect. Okay, now let me do. And this just refed out because, well, because I've entered in because I've reordered things. So here we got to start at day 0. And now everything populates. Great. And we go up to 280 days still. Okay. I'm just going to delete that data there at the bottom. Delete. Okay. Now I've got data starting from January 22nd and I go up, 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 up. Now, I'm not sure really how useful this data is. You know, a bunch of zeros isn't really helpful. In fact, it would make it seem like not much is going on. So why don't I delete those too? Because I'm not crazy about putting a bunch of zeros in my data. It's going to skew things downward. I want to start from when this started. So February 28th is a good starting time. Okay. And now I'm going to pull in day and positive cases, these two columns. I go into my Desmos graph. I press Control V. Ha! Okay. Now we see I've got data in. Desmos has labeled my data as X1 and Y1. So X1 is the days. So we can see on day 200, you know, we've got this many cases. 6.55 times 10 to the 6. So that's 6.5 million cases in total cumulative. If you press this, is there a plus button? Sometimes there'll be a plus button here where you can zoom in and zoom out. So if I move this up like so, right? And then I click this plus button, it's going to zoom me back down to my data. Awesome. Okay. You'll see here something funny going on with the x-axis. 6 times 10 to the 6. 2 times 10 to the 6. This is Desmos's way of trying to fit the data, which goes up really, really high, quick. So you can see, like on day 0, there's 0 cases, but then on day 150, you've already got 4.2 million cases. 4.273 times 10 to the power 6. So 6 meaning 6 zeros, 6 in millions. Okay, so I've now got my data. Fantastic. It looks like this. And now let's go back to here. So find two variable data. Is this two variable data? Well, this is the number of cases cumulative on a given day. So the number of cases growing each day. So here the variables are positive cases, cumulative positive cases, and the day. So there are two variables. Back to here. Okay, so we've got our data, which we think might approximate one of these. Well, what do we think this, before we even just go any further, do we think this is linear? Do we think this is quadratic? Do we think this is exponential? Well, I've heard about this as being an exponential growth virus. It's kind of like the secret problem that we started off the exponents section with, right? If you remember back to that, someone knows a secret and they tell 2 people each day, and those people tell 2 people. That's exponential growth. And if you think of COVID-19, it's kind of like the flu. And if one person gets the flu, they might pass it on to 3 people. And then those 3 people might pass it on to 3 people, and so on and so forth. So based on that reasoning and my understanding of the telling of a secret problem, I think this might be exponential. But I don't know, looking at it, actually kind of looks kind of linear. And well, I mean, it kind of looks like a parabola too. It depends on how you look at it. So my suspicion is that this is exponential, but my brain isn't quite as good as a computer. So I'm going to let Desmos be my computer and actually calculate these things. So let's first try to let's try to carry out a linear regression where we're going to try to approximate this data by fitting a line to it. Okay, and we all remember that the equation of a line is y equals mx plus b. If we don't remember it, I'm telling you that. It's y equals mx plus b. Now for Desmos, though, to do a regression and find a curve of best fit or a line of best fit, you need to change this equal sign to a tilde. And if you don't have a tilde on your keyboard, you can go to the bottom here and you'll see click ABC, and there's a tilde right there. So you do have a tilde in, or a tilde, I don't know how it's pronounced, in Desmos, and it's right there. Also, when I copied this data into Desmos, it labeled my date or day count data as X1. So my days are X1. The number of positive cases, Desmos labeled it as Y1. So I now have to talk to Desmos in its own language. It doesn't understand what Y and X is. It only understands what Y1 and X1 are. And then, once I approximate this, or once I complete that, entering this syntax, you can see it graphs this black line. And this is the line of best fit, or the linear regression, for this green data. Now, why is it important to actually have this? Well, what would I use this for? Well, you can see, in today's world, we want to understand where this COVID-19 virus is going. What is it going to look like on day 300 in the United States? What is it going to look like on day 400 in the United States? Is this maybe where we're headed? And that's 1.39, no, I guess that would be 10 million, 13,946,000. Down here, this is 10 million, approximately 10 million. So we're going from 8.8 million cases up to 10 million cases in the next, sort of 75 days or 60 days. If you believe this linear line, or this line, is a good approximation of the data we've collected thus far. And how do we know if it's a good approximation? Well, we've talked about this R-squared value. The higher the R-squared, the more correlated your line is to the underlying data, right? And the closer to 1 it is, the quote-unquote better it is. Now, not necessarily. Mathematicians are smart, and they can find ways to fit lines to be very, very close to 1. Make this R-squared as close to 1 as possible. But it might not be realistic. And the other thing that this doesn't really tell us is, what's changed between here and here? Well, no one's wearing face masks here, right? And then all of a sudden people start wearing face masks. Maybe that's explaining the dip here, why this went down. Or this is the lockdown, and then the release, when things open up. And then, the wearing of masks. Basically what I'm getting at is things have changed. Factors have changed between the start of COVID and now. Our preparedness is higher. The community, or everyone is working together and wearing masks. Social distancing is occurring. Various things are happening to try and flatten this curve. So this is a good approximation, however, you would think, because it's 0.96. Now I'm wondering if I can get any better. Well, you know what? I know this course has taught me about quadratic equations. So why don't I now have a look at a quadratic equation and just see how well it approximates this data. Now, to type this in, if you weren't in class today, I wouldn't expect you to know this, but this is the code you need to punch in. I just pressed Shift 6 there to get higher up. All right, I'll back up. I'm now typing Y1 tilde is approximately equal to AX1. Then I press Shift and 6, which we call the caret symbol, and that gets me up higher. That gets me up to my exponent, 2 plus BX1 plus C. If you remember, that's the standard form of a quadratic. We like to think about quadratics in what's called vertex form, because that helps us graph them really easily. But for Desmos's purposes, to approximate a parabola, or to create a quadratic regression, or in other words, to make this red line fit this green data the best, this red line is a parabola, and it's of the form ax squared plus bx plus c. Well, what do we notice? The r squared went up. It went up quite a bit, actually. It's so close to 1. I'm very pleased with that. I think the parabola does approximate this data better. There's a couple things I need to mention about this. First, the parabola approximates the screen data better, and you can kind of visually see that. If I take the black line away, you can see this red line goes like right through the green data. Our plotted scatter chart, our green data is the coronavirus positive cases, cumulative. If I put my black line back on, you can see this black line is way higher than this, and here it's lower than the green. So this black line maybe isn't as good as this red line, because this red line looks like it goes right through all the green data. It looks great. But now let's take a step back. Let's just have a think about it. What's going on over here? Does this mean if we rewind in time to before COVID, that we'll find that there's, millions of cases? Well, no. We know that before the coronavirus or COVID-19 came, there weren't any COVID-19 cases. So I don't believe that this left-hand side of the quadratic equation is very useful to us at all. But that's okay. I know that now. I'm saying that to myself. This part of the graph doesn't make sense. But maybe I just say that this side of the graph is good, is a good approximation. And I can see that the r squared is quite high, which tells me that this does fit the data quite well. You may be tempted to just stop there, but we also have learned about exponential equations. So I'm going to try to approximate an exponential equation against my data. I'm going to regress an exponential equation to see if I can get a better line of fit. And an exponential equation, we learned y equals 2 shift 6 to the 2 or to the x. That's a graph that we learned, or we learned 3x. Well, the base form, or the standard form for a exponential equation is a times b raised to the x, caret x. Now remember, to do a regression in Desmos, you need to have the 1 beside the y and a 1 beside the x, and this tilde sign needs to work. Okay. So, I'm going to take away the red line and the black line. Now, I think this looks pretty good. It also goes through a lot of the green data. But you'll notice my r squared dropped. In fact, my r squared dropped below the linear equation. I'm just going to put them all back on now. So graphically, they all go through the green, kind of. But I guess my question then is, which way is the coronavirus going? Is it going this way? Is it going up parabolically or in a quadratic fashion? Or is it growing up exponentially? And now I have to try to make sense of this. I have to try to predict the future with this data. Now, what are some of the things I might say? Well, first off, as a statistician, I need to caveat everything. First off, COVID-19 has never been here prior to 2019, so I don't know much about it. I don't know how it's going to grow. I'm not sure if the measures that are being put in place by different governments are working. And I don't know if they're being executed in the same way. Are people around the world wearing face masks? in a similar fashion? Are the rules the same? Have the lockdown rules been the same? Basically, there's a lot going on all over the world that's going to affect the spread of this, and in particular in the United States. It seems like there isn't a clear direction, and different states are acting differently. So there are a lot of variables at play here. And all we can say is, based on this data, we think the line of best fit is a parabola. Okay, so how does this help you with your assignment? Okay, let's go back here. Create a linear regression, a quadratic regression, or an exponential regression. Explain why you chose this regression model and why it is a good regression model to fit your data. Okay, so coming back here. So we've kind of talked about that already. The R squared ultimately tells me which one fits the data best. But then I need to put some qualitative spin over top of it. I need to use my brain and think about it. Do I believe this? Well, I explained that I'm not sure that the parabola is actually the best thing, because we know prior to COVID being here, it didn't go up. There was no COVID up here. Right? At day negative 400, so sometime in the beginning of, or at the end of 2018, there weren't, nearly 10 million cases. So I need to put some caveats around this. I think this parabola is a good approximation of the data for all values of x greater than 0. So I don't believe that this quadratic is a good approximation for the past. I think it's only good for the future. And I also think that this graph doesn't take into account the measures that have been put in place to increase social distancing, for people wearing masks, to reduce the spread of COVID-19, and to try and flatten the curve. There is a lot of effort being put into trying to flatten this curve. So I think this is the trajectory of COVID-19. I think the parabola right now is a good predictor if we keep going the same way, if we keep doing what we're doing. But we are trying to flatten the curve, and governments are trying to put in place different rules around the world to try and flatten this curve. So there are external factors at work here. It's not just, oh, this is the data and it fits a parabola, and the coronavirus is just going to keep growing and growing and growing and growing. There are other things at play, so I need to be mindful of that. But for this, so these are some of the things that you might want to talk about. This data is only good as how you read it. So I have a really high R squared, but do I think in 800 days there's going to be, or in 1,000 days? Well, I don't know. I mean, if measures aren't put in place, maybe. I don't know. Let me put these back on. But this is how you'd carry out a regression, and you would talk about how this graph fits your data, or how this quadratic regression approximates your data. Okay, so that's step 2. Create a regression, explain why you chose this and why it is a good regression model to fit your data. Make a sensible prediction on your regression findings, justify your response. Okay, so coming back here, we've chosen the one, our graph with the highest R squared, our parabola. And what I might be able to do is predict, where we're now 243 days into this. So a simple prediction I might make is, by the time we reach 250 days, so in the next week, I suspect the caseload might go up to 9.37 million. My next prediction could be, well, I think by day 300, we'll be approaching 12.7 million cases. And that would be my prediction based on the past performance. Again, I need to kind of justify my response. this is my prediction, and mathematicians will use this this phrase a lot, all other things being equal. So if everything else stays the same, this is how I suspect COVID-19 to increase. But things aren't staying the same. As I said, governments are intervening, steps are being made, social distancing, physical distancing, the wearing of masks, etc., etc. Describe your curve or line of regression. This should include.
Please call extension 5621. Kilo Diverso 5621.
This should include a statement about rate of change. Okay. So again, we're still talking about the same thing. What is the rate of change? Well, the rate of change is your rise over your run. So, here I might say, again, I did kind of talk about the rate of change. You can first maybe look at your green data and say, what's happening? Why? Where is the rate of change slowing down and increasing? Well, when the slope flattens out, so here the slope is flattening out on the green curve, right? This is flatter. This is steeper, this green. Go away, Steve. I could maybe say, well, it was flattening out here because this is when lockdown happened. It's increasing here because this is when lockdown stopped. It's flattening out a bit because of the wearing of face masks. That's kind of what I want you to describe your data and its rate of change. Or you can talk about the rate of change in your line of best fit. So a parabola increases by the difference of squares, right? If you think back to your data tables and quadratics, when x is 1, if you look at the graph y equals x squared, then y is 1. When x is 2, well, 2 squared is 4. So y is 4. When x is 3, y is 9. When x is 4, y is 16. So each time you're increasing by, first you increase by 1, then you increase by 3, then you increase by 5, then you increase by 7. So the rate of change is increasing at an increasing rate, but not as fast as, say, an exponential would grow. So to talk about the rate of change, you would look at the delta y over delta x, or the change in the rise over the change in the run. And all you need to really do to calculate that is pick one point on your graph. So this point here, which is 260 and 10 million. And then pick another point on the graph here, 290. There we go. And 12 million. So we went from, what did I say this was? 260 to 290. So our X value went up 30. So our run was 30. And our increase was 2 million, from 10 million to 2 million. So to calculate this slope, it would be 2 million delta Y over delta X. So delta Y here, the change in Y, it went from 10 million to 12 million. So that went up 2 million. And the delta X, or the run, was 30 days. So you divide 2 million by 30, and that'll give you your slope. That is your rate of change per day. Okay. And then describe your curve. Okay, this should include a statement about rate of change. We did. So we've our line of best fit, or our curve of best fit, is a quadratic equation, and the rate of change is just how I described it. Discuss why other models might not be as good as to approximate your data, and why. So here I want you to talk about why a linear model and why an exponential model maybe aren't as good. Well, I think we can again say linear model, this black line, isn't good because this linear model actually says or predicts that on day 10 there were negative 80,000 cases. That doesn't sound right. There were never negative amount of cases on the 10th day. So there's some limitations, and you want to mention the R squared. this is a good approximation because it's a high R squared, but this is better. We want to go with the one that's better. Although keeping in mind that we need to caveat that a bit. This parabola is only good for values of x greater than 0. Okay, as part of your submission, please share your Desmos. Okay, so here the last part then would be, I'd like some sort of write-up to come along with this, discussing each of the steps. And I hope you're okay with this because I hope this was a good assignment because I think the math is largely done by Desmos, and the grading is going to be largely around just your understanding and interpreting of the graphs. You don't have to carry out many calculations. You just have to understand what you're looking at, talk it through, and this is all new. So I will be in class tomorrow on Friday, ready to go through this. And for the people who are at home, if you're up at 8 in the morning, we always start a Teams meeting, so you can join the class and ask questions during class time. I'm also, at school. It's now, almost 3 o'clock. I'm at school all day, so even when I'm not in class, you can still get in touch with me or schedule some time if you're having trouble with this. Mr. Porto and I, you now have 2 teachers in this class, so there's twice the amount of help available, and we're both really happy to get involved. So let us know if you're struggling. Let me know if any of this doesn't make sense, but hopefully this video is helpful. You can come back and review it, and it'll give you sort of a clearer idea of what's expected for this mini project. Lastly, sorry, I was going to finish off by saying, share your graph. Click this button up here, copy the link, and include that as part of your submission. And then I'll be able to come in and actually look at the data you plotted, and look at your regressions. And if you need any help, if you can share your Desmos with me, then I can hop on your screen and work with you at home while we're both in front of our computers. Anyways, I hope this is helpful. Any feedback you want to give me, I'm open to everything. I'm learning, and I want to be as helpful as possible. And if you can let me know of any other way you think this you can learn the material better, please let me know. But hopefully this is helpful, and I will start doing more of these videos as we move to the end of the semester. Hope you're all well, and I'll talk to you all soon. Bye for now.